Hello, ENET 140. This is the start of our Fiore's Chapter 5 section on op-amp practical limits. And this is, again, ENET 140 op-amps, Bellingham Technical College, Winter 2020. So when we left off at the end of Chapter 4, we went through all kinds of super cool circuits that we could make with different negative feedback networks. They gave us good stability, predictable gains, usually predictable input impedances for both inverting and non-inverting signals, voltage to voltage, voltage to current, current to voltage, current to current gain. It was great. And we were able to make some great bomb-proof assumptions about idealized op-amp behavior, namely that both the inverting and non-inverting terminal had infinite impedance, so no current flowed into them, and that allowed us to also say that the potentials at both were the same. And so we were able to establish things like our virtual ground, at the inverting terminal for certain circuit configurations, and apply our KVL and KCL in some creative ways when we had our summing and averaging configurations, both inverting and non-inverting. So for this entire chapter, we're going to step back into the real world, quote unquote, and look at what happens when we don't have quite such ideal behavior and how to use specs in our manufacturer spec sheets intelligently to predict what happens with real op-amps. And we'll get a little bit into how to select the right op-amp for the job given whatever limitations we have and whatever we need in our circuit. So we're going to march right through Chapter 5, picking up just about every one of the sections. So if you're reading the text, please feel free to include that as well. I am taking this probably closer from the Fiore text than I have other sections because each one of these topics is a bit of a standalone. You will see a lot of equations that are basically, here it is. We're not going to be able to derive everything from first principles because many of these concepts draw on more complex circuitry in the op-amp than we're really going to go into. But we can certainly understand the correct way to apply it. Okay. So again, deviation from ideal behavior. We are still going to concern ourselves only with negative feedback circuits, so no positive feedback, no oscillators. And the big differences we're going to look at are gain at frequencies beyond the midband. So Chapter 4 was only in the midband. We weren't considering any of those negative 20 dB per decade frequency roll-offs. Now we will. We're going to look at noise amplification versus rejection. So we're going to zero in again a little bit more on that common mode rejection ratio and how to deploy it. We're going to look at all the different ways in which the inherent capacitance in an op-amp. This is not our coupling capacitors at the front and back end, but the capacitance that is built into the op-amp, what effect it has on input signal frequency and the effect of our input frequency on output. We'll see that in a couple of places. And then we will pick up some equations for the effect of temperature change on output as a variation on DC offset. So we're going to start with number 1 here by defining a term called gain bandwidth product, or GBW. This is something that you will see in your spec sheet, and the effective quantity may also be listed under the frequency for unity gain, and we'll go over why that's effectively the same thing. Okay, most op-amps include what's called a compensation capacitor, and it'll be between the differential amplifier stage, which will tend to be on the front end, and our follow-on amplification and output stages. So it kind of straddles the middle of the op-amp itself. And this is responsible, this one capacitor is responsible for the lagging network behavior that we'll always see at high frequencies. We've gone over this a few times and touched on it, but just to reiterate, you can make an op-amp that does not have a roll-off in gain going from the midband down to DC, but it's never possible to make an op-amp that's going to have sort of an infinite midband region going to high frequencies. You'll always reach a point where you'll start to lose gain as you go beyond the midband and you'll lose it at that 20 decibel per decade, and that's due to our lagging network, the presence of a series capacitor and resistor network. Well, the compensation capacitor is the capacitor in that lagging network, so it was that RC network that we looked at way back in chapter 1, where we derived the equation for the negative 20 decibel per decade roll off in open loop gain from mid-band to higher frequencies. So now we know where it's coming from. And so this graph here is just sort of a reiteration of that concept. So we're back to open loop now. No negative feedback network. So if we were to look at this graph starting over here on the left-hand side, we have a mid-band region where we've got, this is open loop, so we've got crazy high gains, 100 decibel gains up in the mid-band. And then we will hit the upper extent of that, our upper critical frequency, also known as F2. And then our gain will roll down at 20 decibel per decade slope to a point where we have no gain. So it's a unity gain, 0 decibels, or V out over V in is 1. And so the point at which we reach 0 decibels, the frequency at which we reach that is known as the unity frequency, F unity. Okay, a concept we went over in chapter 3 was that the product of the gain at any point times the bandwidth was a constant. So when we introduce negative feedback, and you can follow my little cursor here, we might drop the gain down from 100 decibels maybe down to, say, 20 decibels, and that would be high for a negative feedback network. So we'd lower the midband down quite a bit, but we wouldn't encounter that roll-off slope until much later. So if we lowered the midband down to say 20 decibels, rather than having an upper critical frequency at 10 hertz, we wouldn't hit it until about 10 to the 4th hertz. But the product of whatever gain we had and the point at which we started to hit that roll-off slope, that product was a constant. And we went over that as part of our derivations of negative feedback advantages. And in fact, that was one of those cases where we swapped some of the gain from the open loop condition to the lower gain of a closed loop, but we got something for it. We got a bigger bandwidth. We're back to that concept. Okay, what if we did that to an extreme and we pushed our mid-band gain all the way down to 0 decibels or 1? Well, then we wouldn't hit the slope here until it crossed the x-axis. So that's kind of an extreme of driving this product here, gain times bandwidth, to the point where our gain is 0, so our bandwidth is as big as it can be made. And as big as it can be made is the point at which this slope crosses the x-axis here. So if we found this point, and we knew what this point was, that would be the constant that the product of gain and bandwidth would always have to multiply out and equal. And that is the definition of the gain bandwidth product, and that's why it's called a product, because it's the product of gain, however you want to define it, times the bandwidth, and that's defined by your upper critical frequency. So we're kind of assuming that, it goes all the way to DC. We're only concerned with the upper end. So what this tells us is that for a real op amp, operating with a certain gain bandwidth, if we know what our actual gain is defined by our negative feedback network, and we look up our gain bandwidth product from our spec sheets, we immediately know the upper critical. We know the upper frequency limit of our midband region, and therefore we effectively know the bandwidth. And so we can use that when we're deciding how much gain we're going to get for a given input frequency signal. So we won't always be working with low frequencies. So we'll look at this just a little bit more graphically. So the dotted line in this graph would be our open loop condition. So we've got a very low upper critical frequency. It's fairly close to DC. So we have a tiny midband region. Got a huge gain, tiny midband region. And of course, you know that we're not going to achieve all of that open loop gain anyway, because we're going to be limited by the supply rail voltage, so we can afford to sacrifice some. If we sacrifice some with a negative feedback network and we drive our gain down to a closed loop, that's a C and an L for closed loop, now our midband region extends way over to here, much bigger. Then we join our 20 decibel per decade of frequency roll off until we hit F unity. So this would be a negative feedback circuit. Okay, so we said that we're looking at the product of gain and F2, or upper critical frequency, equaling F unity, which is also the gain bandwidth product. Well, and that was, we defined that back here. Well, we don't always use the same gain that we would calculate directly from the negative feedback network. As it turns out, we need to use a slightly different gain when we're calculating the upper critical frequency from our gain bandwidth, or F unity, same difference in this case, to get our upper critical frequency. We use a special gain that's applied to a noise signal, which would be common to both inverting and non-inverting inputs. And we'll pick up this concept again as we go through a few of our other non-idealities. But be aware that there's different ways to define gain. And for this purpose, we use the noise gain, or A sub noise. And it is literally defined as the gain if you had the same signal coming in on both inputs. And an easy way to remember that is noise is white, it's frequency independent, and it's common. So a gain for a common input is the noise gain. It is always defined as 1 plus the feedback resistor over the inverting terminal resistor, irrespective of how you have the feedback network configured. So A noise is going to be the same as just A closed loop if you have a non-inverting configuration, but if you have an inverting configuration, it's going to be different by 1. The A noise is going to be 1 greater, and it's not going to have a negative sign. But otherwise, it's a pretty simple formula. So you just basically remember that you're using A noise. Worst comes to worst, going to be off by 1, but we can remember to use this. Just remember that this is the gain you use when you're looking at gain bandwidth calculations, and you just grab your 2 resistor values and calculate it. And it'll be the same as your closed loop gain in non-inverting. It'll be a little bit different for inverting. It'll be 1 different. Okay, so as an example, you use a 741 op amp, which is likely if you build anything at BTC, because there's an abundance of those to borrow. It has a gain bandwidth of 1 megahertz. So that means this frequency right here is 10 to the 6 hertz. Okay, and we can find that on a data sheet. If our closed loop gain is 20 decibels for a non-inverting circuit, what is the upper critical, or also known as upper break frequency? Just a word about nomenclature. The upper limit of the midband region, where your flat line gain starts to roll down, has at least 3 names. 1 is your critical frequency, or upper critical. Number 2 is your F sub 2, which you'll see in my notes and in Fiori. It's also called the upper break frequency, and that's where your flat line breaks. It has a slope break or a slope change. And you'll see that in our textbook, you'll see that some in my notes, and you'll see it in other articles and tutorials and possibly in spec sheets. So upper critical, F sub 2, and upper break frequencies all refer to the same thing. So in this scenario here, we've got a feedback network that's giving us 20 decibels in a non-inverting configuration. We know our gain bandwidth. We want to know what's the upper limit of our midband region. So the trick to this is to use, we're going to use this formula basically, but we're going to use A noise. So all we have to do now is figure out whether or not this closed loop gain that we were given, is that the same as noise gain or not? Or do we have to basically add a 1? Well, they told us that this closed loop gain referred to a non-inverting feedback circuit. Well, in the case of a non-inverting feedback circuit, the 1 plus RF over RI is the closed loop gain. So in this case, A closed loop is the same as A noise. So there we go. This is great. We're home free. We can just plug in the numbers we were given, but we do need to convert from decibels to voltage ratio to use this formula. So we take our 20 decibel closed loop gain, which is the same as our A noise, and away we go. 20 decibels equals 20 log base 10 times our voltage ratio gain, and there we have our A noise, and plug in. Turns out A noise is 10. 10 is the same as 20 decibels, and do some algebra. So we end up with 1 megahertz equals 10 times F2. So we divide 1 megahertz by 10, so F2 is 100 kilohertz. So pretty nice wide mid-band region. We're not even going to start rolling off in frequency until we hit 100 kilohertz. So we'll do another one. This time we've got a negative feedback network. So somebody gives us this nice circuit, and we've got obviously a frequency dependent input signal here with our little AC signal, and we've got an inverting resistor of 2 kilo ohms. We have a feedback resistor of 10 kilo ohms, and somebody wants to use a 741 op amp and is concerned about what is the upper end of the midband. Maybe they want to use a different op amp, and maybe they need to extend this region, or maybe they need other characteristics, but we want to know where the upper midband stops. So we need A closed loop, A noise, and the gain bandwidth. What we really need is A noise, but we're going to get it from A closed loop. We could get it directly from these resistor values. So I think the problem here may have wanted to know what the gain was. So we could construct, we'd know what's going on in our midband region. Well, gain is easy. It's negative R feedback over R inverting, which is going to be negative 5. So we got a 5 times increase in voltage output to input, and it will be 180 degrees out of phase with the input. And if we take 20 times log base 10 of 5, we skip the negative because decibel gain doesn't really concern itself with phase. We get 14 decibels, so we could plot that. A noise is 1 plus RF over RI. Well, we know each one of those, so it's 1 plus 5 equals 6. The gain bandwidth for 741 is still 1 megahertz, so we have 1 megahertz divided by 6 equals 167 kilohertz, so a little bit wider. So we don't start rolling off the midband until a little past 150 kilohertz. So you can see that the bigger this number is, the bigger the gain bandwidth is, for a given gain in the midband region, the higher our upper break frequency is going to be. So if you look at more expensive op amps, you might find that you're paying a little bit more money for a higher gain bandwidth, which allows you to carry a higher closed loop gain within the midband and still have the same end of the midband, the same upper limit in frequency, or have the same frequency and then extend the bandwidth. Again, it's a constant product. So we have a little bit of a design problem here. Example 5.3, and again, this is coming right out of the textbook. So we're asked, what is the minimum acceptable F unity, or unity gain frequency, which is the same as gain bandwidth, if the midband has to extend to 50 kilohertz. So somebody said, okay, I need a midband frequency that goes all the way to 50 kilohertz. That's my F2, or F upper break. What kind of gain bandwidth do I need? Well, we need another piece of information. We'd have to ask him, what's your A noise, or what are your feedback and inverting resistors, so I can calculate an A noise, and I'll tell you. And they say, okay, well, here's my circuit. I can say, all right, well, you've got a 500 ohm inverting input resistor and you have a 20 kilo ohm feedback resistor. Well, I can do a 1 plus 20 kilo ohms over 500 ohms and I can get an A noise of 41, which is not necessarily, actually in this case, it is the same as my closed loop gain. So that's convenient, but not necessary to choose the right gain bandwidth. So I go back to my formula, which basically conserves bandwidth and A noise. I put in 41 for A noise. I know that I want an F2 of 50 kilohertz, so I can get a gain bandwidth, otherwise known as F unity, of just a little bit over 2 megahertz. 2.05 times 10 to the 6 hertz. So I need something with double the gain bandwidth of a 741. So I would have to go with a different op amp. So that's just an example of how a property that we need for operating the circuit, don't know why somebody needed that, but that helps us choose the right op amp. Okay. So the next subject, or the next part of the same subject, is what happens when we go to multi-stage. What if we can't get enough gain, maybe with just one op amp, and how does this extension of the midband region work when we got more than one? Well, there's two different scenarios that we can have if we've got multiple stages, and here's just sort of an example of 3 ganged op amps where we've got a frequency variable signal coming into the non-inverting terminal. We've got some feedback network that gives it a gain, and then we're going to amplify it again in stage 2 and again in stage 3, and we're going to have a V out that's of course going to be V out over V in is going to be the gain of each one of these 3 stages multiplied together, the voltage ratio gains. If the upper critical frequency for each of these stages, stage 1, 2, 3, is different, then the system is going to be limited by the lowest one. So if, say, the upper critical, the upper break frequency of stage 1 was 10 kilohertz and stage 2 was 100 kilohertz and stage 3 was 1 megahertz, it would be stage 1, 10 kilohertz. It's whichever one is lowest. If they're all the same, then you have to go back to what exactly was the definition of the upper break frequency. Well, it was the frequency at which the power, the voltage ratio equivalent, power equivalent of the op amp in terms of gain is half of what it was in the midband. So it's the half power frequency. So if you say, okay, well, at that particular frequency, say each one of these 3 has the same F2. So at that F2, my gain, the power equivalent gain of this stage, is half what it is at the midband. Alright, so I could say, I could call this midband gain divided by 2. And so is this. And so is this. Well, wait a minute, the gains are multiplicative. So I'm doing midband gain over 2 times midband gain over 2 times midband gain over 2. So my V out is going to be midband gain over 2 times 2 times 2, or midband gain over 2 raised to the power of however many of these suckers I got. That's a pretty big hit. So for 3, I ended up with an 8 times hit in the gain I would have. So if I want to define a half power frequency, I've got to go back further towards the midband, because if I use the stage F2 in each of these cases and I multiply them all together, I'm going to get something that has far too low of a gain as the output. So I can do some math and basically mathematically replicate what I just said in words, and I'm going to let you guys kind of step through all of that. And I can end up with this super handy expression here, which basically says the same thing. And that is that the upper break frequency for a system that includes n stages each of which has the same upper break frequency. So if n is 2, you got 2 of them with the same upper break per stage. Your upper break frequency for the system is just the upper break frequency for the stage times 2 raised to the 1 over n, where n is equal to the number of stages, minus 1, everything in that square bracket's raised to the 1/2. Like I said, you can step through the derivation. Here it's not that many steps if you're interested in the math, but it basically relies on the fact that each stage will have its own gain at the upper break frequency equal to the midband divided by 2, and that's why you end up with this 2 raised to the 1 over n. So that's our second scenario. If all of our stages are the same, we end up with a system upper break frequency that is less than the per stage upper break frequency by an amount that is in these square brackets raised to the 1/2. Or if all of the stages are different, it's the lowest one. Simple. Okay, so here's an example. We got 3 stages. We got one which is inverting, or excuse me, non-inverting, and it's got a gain of 8, so 1 plus 14 over 2. And then that's followed by an inverting amplifier. So stage 2 is inverting, and it should have a gain of minus 2, so RF divided by 10. So our signal comes in and it gets bumped up by 8 times in amplitude, and then it comes in here and it gets bumped up by 2 in amplitude and shifted by 180 degrees. And then it comes into the non-inverting terminal of stage 3 and it gets amplified by a factor of 4. So that's 12 divided by 4 plus 1, and it pops out. So we know something about the gain of each of these stages, and what do we know about their upper break frequencies? Well, we got to calculate that. Somebody said they're all 741, so we have gain bandwidth. So we'll have to calculate an F2 for each one of them, see if they're the same or different, and either pick the lowest one, or if they're all the same, we'll use this formula. So first we got to get the upper break frequencies per stage. So let's start stepping through that. We got the gain bandwidth, that's part of it, and we can calculate the AV noise because we have the feedback resistors. So for stage 1, 1 plus RF over RI is the same as the stage gain, which is 8. So we can do some math there, set that equal to the gain bandwidth. We get an FC stage for stage 1 of 125 kilohertz. We can do the same with stage 2, just remembering that in this case the AV noise is not the same as the gain of the stage because the stage is inverting, but we end up with an FC stage further out. It's a little higher, it's 333. So if it were just between stages 1 and 2, our upper break would definitely be limited by stage 1. It'd be 125. And we do the same thing for stage 3. We calculate its upper break frequency, and it's somewhere between these two. So lowest number is stage 1. The upper break frequency for the system is the same as stage 1. Lowest one rules. Okay, so we get another scenario. Figure gotta have that other example. So somebody says, hey, I need a multi-stage amplifier. I'm going to have 3 stages, and I'm going to use identical non-inverting voltage stages. Each one of them has a voltage closed loop gain of 10. They're non-inverting, so I know my closed loop gain and my noise gain are the same. So F unity is 4 megahertz, so 4 times what a 741 is. So somebody spent a little more money. They want to know what the system gain and the upper break frequency is. The system gain is easy. We multiply the stage gains by each other, so it's 10 times 10 times 10, 10 to the third, so it's 1,000 times. So there's an advantage right there of a multi-stage system. We get multiplicative gains. And so now we get to use our fun formula for system frequency for similar stages. So we need the upper break frequency for each stage. So we're going to use our gain bandwidth. We're going to use A noise, which is the same as A stage because it's non-inverting, right? So 1 plus RF over RI is both the noise gain and the actual closed loop stage gain. So 4 megahertz divided by 10 is 4 times 10 to the 5th hertz, and that's our per stage gain. So we go to our handy dandy formula for system upper break frequency as a function of stage upper break frequency and how many we got. So we got 3. So we have 2 raised to the 1 over n, where n's the number of stages. We got 3 stages. So we have FC stage, which is 4 times 10 to the 5th hertz times 2 to the 1/3 minus 1. All of that raised to the 1/2 or square rooted, which is the same as saying 4 times 10 to the 5th hertz times about 5. This all works out to about, 0.5. This all works out to be about 0.51. So about 204 kilohertz is the upper break for the whole system. And notice how much smaller that is than the stage. So we lost a bit. So we got, by having 3 stage amplifiers together, we got a big jump in gain, but we had to roll back our bandwidth a bit. So I think this is the last example for this type. This is example 5.6 at a Fiori. So we get a different op amp, the LF411 op amp. So somebody wants to design a circuit and they need a system upper break frequency of 500 kilohertz and they need a system gain of 26 decibels. So they need a pretty good amount of both. So it's a good thing that our gain bandwidth for our LF411 is reasonably high. So we have 3 megahertz. So that means our FC stage is going to be pretty big. So, but nobody said we had to use the same one. We didn't have to use the same stage upper break for each one. So we were kind of open-ended on this. So we could make them different and then just end up setting our system upper break frequency by the lowest one. So the way the book goes over it, and there's, like I said, there's a million different ways to do this, but what the book did was took 2 approaches. One, which was to use kind of one stage of the amplifier and design its gain, its noise gain, such that it set the upper break frequency. It was the low end, and then added other stages with much lower gains and much higher stage upper break frequencies to give us the total gain we needed, or we could go the other way. So just stepping through. So first let's check and say, hey, you know, this is a fairly fast or a fairly large gain bandwidth op amp. Could we do it with one stage? Always worth checking. Hey, keep it simple, right? So if we assumed a non-inverting configuration, our AV stage and our AV noise is the same. Voltage ratio equivalent of 26 decibel would be 20. So if we said, okay, to get the exact gain we need with one stage, we'd have an AV noise of 20. We've got a gain bandwidth of 3 times 10 to the 6 divided by 20. Nope, too small. 150 kilohertz, we needed 500. So we're going to have to go with at least 2 stages. So as an example, well, what if we did 2 equal stages? You know, we could certainly get the gain we need, but if the 2 stages are equal, could we get the gain we needed and achieve our 500 kilohertz? Well, if the 2 stages are equal and we need a total gain, of voltage ratio 26 dB, we'd take the square root of 20 and say that would be the AV per stage, the AV noise, so we could calculate FC stage. And this is the result of that math. So we would then, so we're basically calculating FC stage based on our gain needs, and then dropping it into the two equal stages version of our system with equal upper break frequencies to get our upper break of the system. Can't do it. So that doesn't work, because we'd have to solve these together. So we end up best off using two stages with different FC stage. And I believe that's what Mr. Fiore did in the textbook. So stage 1, we designed around our upper break needs. We said, okay, we're gonna use whatever noise gain, which is the same as closed loop gain because we're non-inverting, that we need to do to get us an FC per stage for that stage of 500. So we just use our gain bandwidth, divide by our FC stage, and then we get the gain that we're going to have for that stage, so 6. So remember, we needed a total gain of quite a bit larger, of 20, so 20 divided by 6, and that might have been an error if I have 26 in there. That's not right. So we set up the second stage to give us the additional gain that we need, and as it turns out, our second stage gives us a much larger FC stage, and so it doesn't limit the system from the standpoint of our upper break frequency. So this is the approach that actually worked the best. We set the FC stage and the gain of one of our two stages, and then just use the second amplifier to bump up the gain that we needed, accepting that with a very small additional gain we would have a fairly large FC stage 2. So I ended up actually working, again, 3 different possible scenarios, and it was the last one that was the easiest and simplest. But like most design problems, there's quite often a large number of possible solutions, so that you will probably not see anything that complicated on your exam, so that would be much more appropriate for a project, and that's where a lot of the fun of design comes in. But that just gives you an idea of how you can rock the needs of a system between gain per stage, total system gain, and then what's going to set and limit your upper break frequency. Okay, we've been talking all break frequency being upper break frequency, so just as a word, remember that the lower end of our frequency going down towards DC, you can have op amps that are either designed to maintain the mid-band gain all the way down to DC, in which case that compensation capacitor that we discussed as having been responsible for this 20 decibel decrease in gain off the mid-band per decade of frequency, that might be absent. We may not have that. And some op amps are designed to allow you to basically put one of your own in, which would then tailor that roll-off region with frequency however you want it. So that's those are special types of op amps that are designed with that kind of flexibility. I would not use that without caution, because obviously the capacitor gives you some amount of stability, so I wouldn't dispense with it frivolously, but know that that's out there. If you're using an op amp that is not what they call direct coupled, that doesn't maintain the mid-band gain all the way to DC, everything that we went over for the upper break frequency would correspond to the lower break frequency, or the low frequency end of the mid-band region, beyond which your gain is going to start rolling off at 20 decibels per decade downwards. And again, the only difference is that you would be looking at a lower frequency, not a higher, because you're going from the mid-band frequencies down to DC. Okay, we are going to pick up one more topic and then take a break, because this is a very, very long chapter, and this is related to capacitance. So we're gonna pick up one more topic here that's related to time rate of change of a voltage signal, and this is called slew rate, and many of you may have already encountered this as a property of op-amps and related devices. And then power bandwidth being another characteristic related to time rate of voltage change that kind of goes with slew rate when we're talking about an AC signal. So if we go back and we think about this compensation capacitor, this capacitor that's situated somewhere in our op-amp that pretty much every signal that goes through the op-amp has to pass through. We've used it to establish the upper break frequency, and we've looked at it from the standpoint of an AC circuit. We can look back at the basic definition of capacitors, and we relied on these relationships here when we derived that 20 decibel per decade frequency roll-off region. Our lagging and leading networks relied on the differential equation solutions from these two relationships. But if we take a look at these in just their simplest form, current is equal to capacitance times the time rate of change of voltage, or dV/dt. We can say dV/dt, or the time rate of change of voltage, is equal to current over capacitance. If we think about this capacitor being somewhere inside our op-amp and the op-amp having some kind of current signal going through it, we could do some measurements maybe, or do some calculations on the op-amp circuit, or model it, and then find the maximum dV/dt that op-amp could carry based on the maximum current that flows through it and the size of that compensation capacitor, or the maximum current that can flow through that portion of the circuit. So it's not hard to imagine, given that we already know that quite often our op-amp output current, for instance, is limited to 20 milliamps, that there are other portions of the circuit that have a limited current, and we know that most of our frequency response characteristics of our op-amps are a function of that compensation capacitor. It's not hard to think that there's going to be some upper limit combination of current divided by the compensation capacitor that is going to limit the time rate of change of voltage that op-amp can faithfully reproduce. Okay, so that upper limit in dV/dt, or time rate of changes voltage is known as the slew rate, or the upper limit of voltage slewing, SR, and it's a spec property of the op-amp. We can just look it up. It's typically listed in units of volts per microsecond. So that's the fastest voltage change that the op-amp can effectively follow. So that's pretty easy. The trick comes in applying it and understanding what time rate of change of voltage we're asking our op-amp to follow, and then making sure it's the output. Because obviously if we have a certain amount of voltage gain as a result of our op-amp, and we have a constant frequency, we're not changing the frequency as we go through the op-amp, the delta V over delta T is going to get much bigger when the delta T stays the same, but the delta V increases because we've got a certain amount of gain. So the textbook gives some fabulous graphs that show a square wave going to a trapezoid and eventually a triangular wave signal as the result of slew rate limitations. And I'll try to walk through a few of these here in the notes. I haven't reproduced all of them because the textbook pictures are just really, really good. So if we imagine that we have in the dark line, the solid line, a square wave pulse signal. So at T1 our signal goes up, we have our V1 max voltage, and then at T2 it drops. If we imagine this is obviously a dV/dt of infinity. If we defined another T here, TA, which of course wouldn't be applicable if we're in the real circuit because it wouldn't start responding until we got to T1, but we could define a TA and say the difference between T1 and TA would be the delta t that you divide 0 by v1 at, and this dashed line would represent the effect of a slew rate maximum. So if our op amp couldn't tolerate a voltage time rate of change greater than T1 V1 over T1 minus TA, you would effectively get a trapezoidal waveform instead of a square waveform on your output. The ultimate limitation on this is if we have a much higher, narrower pulse, high frequency, high gain. So we have a big V and a T2 minus T1 very small. So if you think about taking this rectangular pulsed signal that is coming out of the op amp, it's our amplified signal. If we wanted to have one spot where the output of the op amp faithfully replicated our max gain of V1, it would just be that single point. So we would say, okay, what's the slope that corresponds to that? So how fast would our op amp have to move to go from 0 volts to V1 and then turn around and come back to pick up that one spot on the signal? So basically you can divide that rectangle in half and say you would end up having a slope that your op amp would have to achieve, or a slew rate your op amp would have to achieve, that's equal to V1 divided by a delta T that's equal to half of T2 minus T1. And if you did that, you would achieve a triangle that just touched. If you drop below that, you'll end up with some triangular waveform that's significantly less than what your closed loop gain would have otherwise given you. So this is interesting now. A slew rate, or a dV/dt limitation of the op amp, could give us a lowered output signal and what appears to be an inadequate gain, and it'll change the whole waveform. It'll take us from a rectangular or square wave to a triangular wave. So that's a lot of distortion. So if instead of sending a square wave in, we send in a sinusoidal wave, which is going to be more typical for signals and certainly for something where we're defining power, we can look at this even more simply, because on a sinusoidal wave we can define the point and the magnitude of maximum slope using a little bit of calculus. And again, for those of you who haven't taken calculus or won't be taking it, you can just skip right down to the formula that we're going to derive for you. So if you have a voltage versus time signal that's sinusoidal, and it's some amplitude k times sine of 2 pi times the frequency times time, which is pretty much our standard sinusoidal voltage signal. If I took the first derivative of that, I would get 2 pi times k f times cosine of 2 pi times ft. So this is the rules for derivatives of sine and cosine trig functions, and that's the slope. That's how fast the voltage signal is changing with time. And notice it's not constant. So at t equals 0, it's actually changing the fastest, and at t equals any multiple of pi, it's going to be changing the slowest. So our maximum comes when this cosine term is equal to 1. So we can use that fact to define maxima of our time rate of change of voltage. Our dV/dt maxima can be expressed as 2 pi times the voltage amplitude of the original sinusoidal voltage signal times frequency. And that came right from this term right out front of here, assuming that the maximum value that this part can assume is 1. So this is our maximum. This is the maximum slope that the function assumes, right? 2 pi times the amplitude of your sinusoidal function times its frequency. Higher amplitude, higher slope, higher frequency, higher slope. If the slew rate of your op amp can't meet this, you're going to start chopping it. You're going to start getting distortion of the waveform, and you won't get your full gain out. So this is a bit of a benchmark when you're looking at selecting an op amp, and you know what your sinusoidal voltage input is, and your output will just simply be the gain times that K, and you know your frequency. One check to make sure you get an undistorted signal and you get your full output gain is to make sure your slew rate is at least this big. So here's what happens in terms of what you might see on an oscilloscope if you chose an op amp that did not have a fast enough slew rate to keep up with the max slope of your sinusoidal output function. Remember, this is your output. If it didn't keep up with your input function, you're going to be in a world of hurt more on that amplified signal because the K will get bigger by your gain. So what'll happen is on your output, what you were hoping for was this beautiful dotted line, this nice amplified voltage signal. But what you're going to get is the solid line. You're going to only get a slope as big as the op amp can give you. This is the max slew rate. It says, well, my max dVdt is this. So it's going to stay positive until it hits what the output function is really trying to do. And at this point, it's going to go, oh, you want me to change slope. Now you want me to head downhill. So it's going to head downhill, and you can't see it on this graph, but it's going to head downhill at the same slope it was heading uphill, which is going to be shallower than your main function. So it's going to miss it, and it's not going to pick up again till here. And what you're going to end up with is a triangular waveform with an amplitude that is much lower, usually much lower than what you had hoped for. So if you are you're measuring something with op amps and you're doing a lab or you're doing a project and you see a triangular wave output where you expected a sinusoidal and it's maybe half the amplitude you expected, check your slew rate. You may not be effectively keeping up with the slope of your output voltage versus time. So here's just a quick example. This is example 5.7. You've got a 741 op amp, somebody's using it to control a motor. The motor control needs 3 kilohertz at a 12 volt peak. So will we get slewing? Will we get distortion? Okay, so we'll assume that the motor control, this is a motor, so we're assuming that things are sinusoidal. Motors and generators generate sinusoidal or use sinusoidal signals. So we're going to go back to this formula that we just derived. So we're going to say, okay, what does the motor need? Well, dVdt is going to be 2 pi times our V peak, which was 12, times the frequency, which is 3 kilohertz. So that's 3,000 cycles per second. And this is 2 pi radians per cycle. And so that gives us 226 K volts per second. So we can compare that to the 741 typical slew rate of 0.5 volts per microsecond, do some adjustment to volts per second, and we see that our 741 will give us 500 kilovolts per second. No problem. I have the capacity for double the slope that I needed here, so I'm good. No slewing is expected. Another example here, we need 20 kilohertz with a peak voltage of 10. So I can do the same analysis and say, okay, this is, I am assuming without, if I'm not told otherwise, it's usually a good idea to assume it's a sinusoidal signal. If all you hear is a frequency and an amplitude, assume it's sinusoidal and not triangular, square wave, or whatever. So I'll assume that, and that means I can use my max slope of my signal. Max voltage versus time slope is 2 pi times the amplitude times frequency. So that gives me 1.26 times 10 to the 6 volts per second, which could also be expressed as 1.26 volts per microsecond. That's the minimum acceptable slew rate. The 741 only had 0.5 volts per microsecond, so that wouldn't be fast enough, but these other two op amps would be plenty fast. So you can see how my slew rate is driving my choice of op amp independent of gain bandwidth and all those other properties. So a little bit of a design consideration. And what if we have multiple stages? So this little chart kind of graphic is similar to what's in the book, and it just gives you a little bit of a guide of what's going to limit our slew rate needs if we have multiple stages, and it's based on gain. So the general rule is the back end has to be bigger than the front end. And the big reason for this is the frequency is not changing, but the amplitude is. So we have a signal of whatever amplitude coming into stage 1. We have to choose a slew rate that is big enough to capture the whole signal. So if it's sinusoidal, we'll go through our dV/dt is 2 pi times the peak frequency, or times the peak voltage, times the frequency. We'll choose an op amp that has the appropriate slew rate. Now we're going to amplify it. So now that peak, if it were, say, this case, it's not 10 volts anymore. It's 10 volts times the gain of that stage. So stage 2 has to have a slew rate that's as big as stage 1 times the stage 1 gain. So, that's it may or may not make it. You may get some distortion. So what stage 2 is going to give you is the output of stage 1 times stage 2 gain, or its max slew rate, whichever's lower. Presumably, either one is going to be bigger than the original input signal that came into stage 1, and that's going to be ported over to stage 3. So you can see the little if or that takes you through. But basically each stage has to be able to respond to a voltage per unit time change that's equal to the original signal times the gain of all the previous stages, or the max slew rate returned by the previous stage. So each stage has to be faster. So you can just go through that exercise to know what your slew rate minimum is going to be for each stage based on what you picked for the stage before. And so ideally you wouldn't be distorting. You would be going from you would be going for AV1 times your signal input characteristics for your output, and you would then multiply by AV2, and then your slew rate in stage 3 would have to handle AV2 times AV1 times AV3 times the time rate of voltage change of your initial input signal, if you wanted to avoid any kind of slew distortion. So you can just choose that. Okay, we're going to end the lecture here. We'll probably have 2 more recorded lectures. We've got another 7 pages, so we've now covered all of the characteristics of real live op amps that are mainly due to that middle of the op amp compensation capacitor that controls frequency characteristics. So gain bandwidth, limits on the upper and lower end of our mid-band gain region, definitely frequency related, and then slewing rate is all about frequency. It's all about time rate of change of voltage. Next lecture we're going to jump into offsets, which go back to the DC world, and what we do in adjusting from a DC standpoint, going back to the concept of biasing, and how non-idealities in biasing can introduce a DC offset to either a DC output or an AC output that we didn't want, and how that introduces uncertainty and error, especially in an instrument measurement signal that's coming in that might make it impossible for us to measure something, which would be really bad. So that will be the next subject. We'll look at how temperature changes affect, offsets beyond the effect of just the non-idealities that are going to show up in the spec sheet. And then after that, we'll take a look at common mode rejection ratio and noise, and that'll be it for chapter 5. So we're going to head into DC, temperature, and noise in the next 2 lectures. Stay tuned, and thanks.